Today we're going to talk about topic 5.4, which is called the fundamental theorem of calculus. And we are going to break this down into some smaller chunks and look at it over a couple of days. So these notes are specifically today for day one. It's obviously an important theorem. It's called the fundamental theorem of calculus. And we're going to kind of dig into that. So first off, let's kind of recap. So we're going to start with these two graphs right here. And I went ahead and gave each of them a name, g of x and f of x. I think they pretty much had a name at one point, but I don't know if when I PDF'd it, they slid behind my graph or not. So we'll just kind of look at it from this perspective. And so if I wanted to find the area under this curve, then looking at the shape of the area, so let's make sure we're looking at the same boundaries. So let's go to this one, and I'm going to go from 1 to 3. So the area under the curve between those two markers, which means it's a definite integral because it does have a boundary. So I'm going to use my integral symbol. I'm going to go from 1 to 3. The name of my function is g of x, and then I have my dx because we need to have our integrand and our variable of integrations, and we need to have our widths and our heights. Okay, so if I were going to do this then, based on the shape of this graph right here and right here, when I go about finding that, what technique would I use that we've looked at so far? Well, that would be where Riemann sum comes in. So we could do right Riemann sum, left Riemann sum, midpoint Riemann sum, or we could do trapezoids. But if we're going to do that, then when we find this area, so we would use Riemann sum. And all of that is going to be an approximation, right? We're going to approximate the area under the curve using one of our Riemann sums or trapezoidal sums to find this area, okay? So now let's look at the second one. So let's go from the same place from 1 to 3 of this graph. And so if we're going to set up the definite integral for this, we would say the integral from 1 to 3 of f of x, and then I would have my dx. So when I'm finding the integral here, is it going to be exact or an approximation? To find the approximate area under the curve here is going to be exact, and we can use geometry to find the exact area. Because what is this shape when I drew my line here? I turned it into a trapezoid, and we have an area model that we can use to find the area under a trapezoid. So approximating with geometry, if you have a specific shape, is going to be exact. Accumulating the area under the shape, if we use Riemann sum, is going to be an approximation. So the difference in an exact definite integral and approximation definite integral. So as we're calculating this area, keep in mind that, we bounded it. So we went from one boundary to the next. So that's kind of important. So the fundamental theorem, why is it such a cool thing? So let me give you a picture over here. So we've got a graph that's going up and it comes back down and then it's going up, maybe keeps going, something like that. So if we wanted to find the area under the curve between any places, so let's say we go from whatever that unit happens to be to where it intersects here, then remember the area under the curve goes between the function itself and the horizontal axis. So this boundary is going to stop that line right there. It's going to be all of this space right here for this part, right? So then that would be my positive area. And then I also have this area down here that's below, that's between the axis and the function. So it's this part right here. And because that is below the x-axis, that would be a negative area. And so then if we were going to try and find the area under the curve, we would find the top area and we would subtract the bottom. And that's how we would find that total area. So the thing about what we're doing now with the fundamental theorem is we don't have to worry about that. The fundamental theorem will take care of whether it's above or below in the process. So we're going to use it to find an exact signed area, so an exact assigned area or place on the graph that's bounded by the definite boundaries, the a and the b, the function, and the x-axis. So that's kind of what we talked about a moment ago, that we're also now going to be doing that with the fundamental theorem. So with the fundamental theorem, there's basically three processes. So one, you have the definite integral that you're finding the area of. And to do that, you're going to find the antiderivative. So remember, antiderivative is the large F. So when you see this, that's the large F. And then once we do that, that's this part right here. Then we're going to find the bounded area. And so to do that, we're going to take and evaluate the upper bound in the antiderivative, the lower bound in the antiderivative. So we're going to do that and we're going to subtract them. And when we do that, this is interpreted as the change of quantity over the integral. And so that's the process that we're going to be doing. So on this first group of problems, we're going to rough sketch what we're looking at. These are all things that you know from your different math classes, and then we'll go about finding the area. So once again, remember when we find the fundamental theorem, it's going to take into account the above and the below, so we don't actually have to split it up. Also, if it's an indefinite integral, then that's when you have your plus c. And the reason we need the plus c is because we might be taking a derivative of something that could have been a constant. When you took the derivative, it goes away. So we don't need the plus c right now because we're going to be looking at definite integrals. Okay, so the first graph here is just looking inside at the function itself, is a quadratic. It's been shifted down 3. So we're going to graph the quadratic. It's been shifted down 3 units. So we should all know what that looks like from Algebra 1 and Algebra 2. Okay, so the next thing I'm going to do then is look at my boundaries. So I have an upper bound of 2 and a lower bound of 1, and that's where I'm going to cut off my graph. Okay, so now that we have done that, remember it's bounded between those two vertical lines, the function and the x-axis. So I have just a little bit above the x-axis here, and I have just a little bit below the x-axis here. And it looks like, or it appears to be, more of the area below than above. So keep that in mind as we move toward an answer. Okay, so now we kind of know what the graph looks like. We've kind of looked at the area that we're going to be finding the area accumulation of. Excuse me, I kind of got a little tongue-tied there. And so how we do this, the first part is finding the antiderivative, right? So we're going to find the antiderivative of the function. So here's my function. So when I take the antiderivative, I'm going to add 1 to the 2, and that becomes a 3. So I'm going to have 1/3 x cubed minus 3x. And then I'm going to show you this one with a plus c, and you'll see why it's a big deal right now. And then I'm going to evaluate it from the top bound on the top to the lower bound on the bottom. Okay? So what I'm going to do here then is put the 2 in for all of this, and then the 1 in for all of this, and do that computation. So I'm going to do 1/3 times 2 cubed minus 3 times 2 plus c. So I have all of that, and then I'm going to subtract the lower bound. So I'm going to have 1/3 1 cubed minus 3 times 1 plus c. All right. Now, like I said, I'm just going to work through it with a c on here, but I wanted you to be able to tell why. We don't necessarily need that plus c at this point. All right, so both integrals are of y, so they are kind of the same number, right? So, or from x, excuse me, and that represents y. I kind of said that backwards. All right, so let's calculate our numbers here. So then I'm going to have 2 cubed is 8. 8 times a third is 8 thirds. And I'm going to have minus 6 plus the c. And then I'm going to subtract. And so I'm going to have 1 cubed is 1 times a third is 1/3. And then a minus 3 and a plus c. So in order to be able to combine these together, I need to distribute that negative through. So I'm going to have 8 thirds minus 6 plus c minus 1/3 plus, change that sign when I distribute through, plus 3. And then I'm going to have a minus c. All right, so as I am working through this problem, then I can see that my c's are going to cancel out because a constant minus a constant, so that's gone. I'm going to have 8 thirds minus 6 minus 1/3 plus 3. And so if I do this side, I'm running out of room, so I'm going to come right back up under my picture up here. And I'm going to do, get 7 thirds there minus, and over here I have 1/3 plus 3/3, so 9 thirds minus 1/3, so that's going to give me minus 3. And so I can find my total area here to be negative 2/3. And remember when we were analyzing our area, so I know this is kind of crazy here, but I went from here, right around here to here. Hopefully that helps. So when I see that I have that area of negative 2/3, did it make sense to the problem? Well, it looks like there's a little bit more below, which would be negative, than there is above. So it does make sense that our final answer would be negative. So ideally we would be going down, but I took up a little extra space to do the graph. So that kind of ate into my workspace. So I hope you can follow that okay. All right, so let's go on to number 2. So if we're graphing number 2, so then we have a square root that's been vertically stretched by 3. And so that's going to look like maybe kind of something here where it's going to kind of go and be taller this way. And then it's bounded from 1 to 4. So then we would be talking about this area under the curve, or between the curve, between the two boundaries and the x-axis. So we would be talking about that area right there. That's where we're trying to find the area up. All right, so this is going to be x equals 1 and x equals 4 according to my bounds. All right, so when we go about working this problem, remember that we need to rewrite it. So let's put a little line down through here. I'll change color ink so you can keep track of what goes with what problem. And so I'm going to do the integral from 1 to 4. And then I have a 3x to the 1/2 dx. All right, so as I'm doing that, then I know normally we can pull the number out in front for things like that, but this is pretty straightforward, so I'm just going to evaluate it here. So when I have x to the 1/2, I add 2 over 2 to the 1/2 so I can add the whole, and so I get 3 over 2. And then when I multiply down, I'm going to take 3 times 2/3, which is going to give me 2, and then x to the 3/2 that I just multiplied down with, and then I'm going to evaluate that from 4 to 1. Okay, so now I'm at my evaluation point, and I'm going to be plugging all my stuff in. All right, so I'm going to do 2 upper bound 4 to the 3/2 minus 2 lower bound 1 to the 3/2. So I get the square root of 4, which is 2. 2 to the 3rd power is 8. 8 times 2 is 16 minus. Square root of 1 is 1. 1 cubed is 1. 2 times 1 is 2. And so my total area here is going to be 14. I don't have any units, so I'm not going to worry about units, whatever they might be, but that's this area under this curve right here from boundary here to here. All right, so you're starting to get the gist of the fundamental theorem. I hope. Okay, so then 3 is the secant of, secant squared x dx. So we have all of this as the function right here. Dx, it's going from 0 to pi over 4. So we need to figure out what the antiderivative of secant squared x is. The antiderivative of secant squared x is tan x. And then I'm going to evaluate that from pi over 4 to 0. So as I'm working through my process here, then I'm going to say tangent, I'm going to go ahead and write it down, I think. Tangent of pi over 4 minus tangent of 0. So tangent of pi over 4 is 1 minus tangent of 0 is 0. So that equals 1. All right, so it's a definite integral. If you're doing something like this, positive or negative, you can kind of think about, you could even do a tangent with a little wiggle and you'd see a little bit of the area above. All right, so this last one is a little interesting because it's an absolute value. And remember, absolute value is not a function in and of itself. It's a piecewise function. So when we do absolute value, we're going to treat it like a piecewise function, not the function model form of it. And we're going to break it apart. Because if you remember, absolute value has that point in it, and we can't differentiate at a point. So we're literally going to break this thing up. So in order to be able to graph this 0 to 2, then I need to isolate my b value inside. So that's going to be the absolute value of 2. I factored out a 2, and I have x minus 1/2 there, and dx. So all I did was just rewrite the form, taking out that b, so I can actually not have any transformations that are masked. All right, so I'm going to graph this right above here. And so we have, if I put in at 0, and then I'm kind of going to go to 2, just so that I have my graph laid out the same way. 1, 2, okay. So if I put in some values to be able to plot this, think about what values you might use. So how I would go about this at this point is I would look and see where is the transformation. So once you have this isolated, then you know your graph has moved to the right 1/2. So this transformation right here, we've moved over 1/2. So if I want to know what's going on the lower bound, which is 0, then I plug a 0 in here. I get 0 minus 1/2 is negative 1/2. Negative 1/2 times 2 puts the y value here at 1. So at 0, my graph is right here. At 2, 1, 2, I'm over here. So remember, my graph has stopped here, and I need to know how far up this is going to go. So I put my 2 in here, and I do 2 minus 1/2 times 2, and that puts me at 1, 2, 3. So that puts me up here at the point 2, 3. So now if I connect these dots, I have this one going here, and I have this one coming in right here. And so remember my upper bound and my lower bound. So at 0 and at 2, then I'm looking at the area under the curve. If we're going here, and here. So that's how it's going to be broken up. So anytime you see the absolute value with an integral, we're going to break it up. So we're going to identify any transformations so we can kind of figure out what the graph is going to look like, evaluate it at the endpoint so I can see what's going on here and here. And we're going to use geometry to do this, because at 1/2, it just split my shape up into two triangles. So we're going to write an integral statement that represents both triangles. So this one is going to go from 0 to 1/2 of, and then I'm going to be looking at, I can go back up here, but I'm going to be looking at the negative 2x plus 1 dx. And then I'm going to add to that the integral from 1/2 to 2 of 2x minus 1 dx. So in essence, I am showing with this negative, I've got my negative slope in this right here, and then I've got my positive slope here, and it's broken apart at 1/2. So from 0 to 1/2, and then from 1/2 to 2. And then we can just do the math for the area of each triangle. Okay, so then I went into this triangle, did 1/2 base times height, and I got 1/4. I went into this triangle and said base, which is 1/2 times the height, which is 3 times 1/2, which gave me 9/4, and 1/4 plus 9/4 gives me 10/4, which simplifies to 5/2. So I did work it out using fundamental theorem so that you could see. So if I did this and I would split it apart like we talked about, and then I would have to find the antiderivative here and evaluate it lower or upper bound minus lower bound. And then I'd have to find the antiderivative here and then evaluate it upper bound minus lower bound. So then I have this calculation to do, and eventually it's going to work its way down to the same answer. So it's the same process as using geometry, but sometimes in absolute values, it is easier to do the geometry because your absolute values are just going to be broken up probably into linear functions, and you might have some really nice, easy, straightforward things to find the area of, like we did here, which were just the triangles. Okay, moving on to problem 5. Find the area of the region bounded by the graph of that quadratic, the x-axis, and the vertical line at 0 and 2. So I went ahead and graphed some of the first ones just so you could get in your mind an idea of what you were trying to find, but not everything needs to be graphed. And in essence of time and space on this one, we are just going to set it up and go all the way through evaluating top bound minus bottom bound. And we'll kind of go from there. So take a minute, do your first and second read, wrap yourself around your mind around the problem. So as we work through this problem, we must have an integral statement. So the integral statement is going to be from the lower bound, which was 0, to an upper bound, which is 2. The function here that I'm going to be using is 2x squared minus 3x plus 2. And then we're going to put those in parentheses because it's a list of terms, and then we're going to put dx. So that is just setting up the integral based on the information given in the problem. Okay, so to go through our fundamental theorem, now we need to find the antiderivative of this. Okay, so I'm going to add 1 to the x, makes that a 3. I'm going to divide down, so I get 2/3 x cubed. And then I'm going to add 1 to the 1, so that makes it a power of 2. And I divide down, I'm going to get minus 3/2 x squared. And then when I have a 2, remember that's the same thing as x to the 0. So when I add 1 to it, I now have an x, and this is going to be plus 2x. Then I'm going to do my evaluation line here, and I'm going to go upper bound 2, lower bound 0. So when you're doing this next step, remember step 2 is to evaluate. So we need to be sure we have the notation here that's showing we're evaluating. All right. So now that we've done that, we're going to plug in the upper bound minus the lower bound. So we're going to get 2 in for the 2 right here. So 2 cubed is 8. 8 times 2 is 16/3. And then we're going to put the 2 in here. 2 squared is 4. and negative 3/2 times 4 is going to be minus 6. And then 2 in here, 2 times 2 is 4. And so that's my upper bound. And then I'm going to subtract. I'm going to evaluate again with the lower bound. So if I put a 0 in here, that zeroes out. If I put a 0 in here, that zeroes out. And if I put a 0 in here, that zeroes out. And so that's my lower bound. I know that it is not necessarily needed to put 0, 0, and 0, but as we build on things and as we add and get more complex, sometimes just putting the zeros down kind of holds a place and it keeps you from not making a mistake. Don't always assume that just because it's a bottom 0 that it's going to actually zero out, because it could have been you could be putting something in and it doesn't necessarily do that always. Some weird numbers, but it can happen. So at this point then, if I were going to get my area together, I would do 16/3 minus 6 plus 4. Take a minute, calculate that, and see what you get. I hope you got the same thing that I did, and I got 10/3. And yes, you're going to be expected to have to deal with these fractions without using a calculator. So you need to practice and make sure you're getting your skills up. As far as this particular type of problem, if you didn't need the area for something else, then this right here would be your safe. You could use that as a safe stop. But if you need to finish that for a value further in the problem, even if you could safe stop, then it's not a legitimate safe stop. All right, so take a minute, read problem 6, wrap your mind around it. Okay, so we've read through the problem. We have a good sense of what's going on in this problem. So then we are going to set up our integral. So you're going to have the integral that's going to go from the lower bound to the upper bound. And you're going to have in parentheses this time because that's a string of terms. So you're going to have x plus sine x dx. I know a lot of times when it's a trig function, we may not need that, but anytime you see that plus or minus and you have a list of terms, everything needs to go in the parentheses, because if not, then you're just saying figure out what x is and then add the integral for this, because the dx would only be attached to the sine x. Okay, so now we're going to have, now that we have our integral statement, this time we're going to do our antiderivative and evaluate. So when we take the antiderivative of x and add 1 to the x power, that's going to be 2. So that's going to be 1/2 x squared. And then the derivative of sine, or the antiderivative of sine, is negative cosine. And then we're going to evaluate it, an upper bound of pi and a lower bound of 0. All right, so when I plug in my pi here, I get pi squared times 1/2, or pi squared over 2. And then when I plug in my pi here, remember I'm saying minus cosine pi. And so that's everything for the upper bound. And then I'm going to repeat the process for the lower bound. So when I put a 0 in here, that's going to zero everything out. And I'm going to have that 0. And then what if I 0 in here? Cosine of 0. So you would be able to figure that out, because that would just be 1. And then it's going to be negative. So upper bound, put the pi in, lower bound, put the 0 in. We cannot safe stop here because we cannot leave any trig functions unevaluated. So then the cosine of pi is 1. The cosine of 0 is -1. I'm sorry, is 1. And then we have the minus from the problem. So now I have a negative negative when I distribute that through, or a positive. So my final answer, pi squared over 2 plus 1 plus 1, or plus 2. And that would actually be the first place that you would be eligible to stop, to safe stop in that particular problem. All right, so go ahead and look at number 2 and get reacquainted with that piecewise function. Pause your video. Okay, so as you looked at the piecewise, hopefully you noticed that the break in the piecewise is happening right here. It's going to where your x's are greater than 0 and then your x's are less than 0. And so when we're evaluating this area from -2 to 3, it goes over that point where this graph is kind of breaking. So what we're going to do is we're going to take this and we're going to break it apart at 1 as we write the integrals down. Okay, so then we're going to go, which side is going to be the ones that are less than 1? That's this bottom one right here. The x is smaller than 1. So we'll start there, and we're going to go from our lower bound of -2 to our upper bound of 1, because that's where this is breaking in the graph right here. And then we use this bottom function, 3x squared dx. Now we're going to add to that the second part, which remember we said it was breaking at 1. So these are all the values that are bigger than 1. So then we're going to go at the 1, and we're going to this upper bound on the original integral, 3, and then it's 6 dx. Okay, so what I want you to do now is go ahead and pause the video and calculate your inputting your upper bound minus your lower bound and getting your area. Okay, so hopefully you're going to excuse me, I got tongue-tied. You're going to use your rules that we've been learning, the ones that are on the green cardstock, to help you get through this. And then you're going to evaluate the top bound minus the bottom bound. And so when you are evaluating that, don't forget you're going to have this evaluation for each of these integrals. Okay, pause your video and let's come back in a moment and compare and see how we did. Okay, so we broke up the first interval, the second interval. So when I found my antiderivative here, I got x cubed, and I'm evaluating from an upper bound of 1 to a lower bound of -2. And then when I integrated 6, because remember this is 6x to the 0, so when I add 1 now I get 6x, and then I'm going from an upper bound of 3 to 1. So then I plug in my 1 to here, and I get 1 cubed is 1 minus, and then I evaluate it with my lower bound. So -2 cubed is -8. So then we have a 1 minus -8, which is 9. Then on this side, I'm plugging in my 3 first. So that's 18 minus, and then I plug in my lower bound, which is 6. So 18 minus 6 gives me 12. 9 plus 12 gives me an area of 21. And again, since there's no units, then our answers won't have units either. All right, so moving on to this next part. Change in position is the displacement, and it's of an object over a closed interval from A to B, VT dt. Okay, so we're looking at this. And then total distance traveled by an object over the interval then is from that closed interval. Notice the difference here is absolute value. So total distance is absolute value. Displacement or change in position is just your integration there. So if velocity as an integrand is a definite integral, then remember the definite integral represents the change in position. So if it's a definite integral and it's an absolute value of velocity, that represents the total distance. So it doesn't matter back, forward, that kind of stuff to be able to think through the problem. So I can drew just a little graph over here so we could kind of review some things that we've talked about. But if it's positive velocity, remember, then I'm going to be moving to the right or up. So for instance, as I'm moving up here, this is up and to the right. If I'm going this way, then I'm moving down and to the left. And then if I'm moving this way, I'm back up and to the right. So remember, when we're talking about that area underneath, we're talking about this, we're talking about this, and we're talking about this. So if it was the absolute value, well, as is, then I would worry about my two positive areas, and then I would subtract off my negative. But if it's absolute value, then it's almost like thinking about bumping that part that's below up above here, right? And so then if we're finding the total distance, it would be this part plus this part plus this part, which is why we have the absolute values if we're talking about that total distance. So the absolute value of f of x is the total distance, and it's like reflecting that up above that x-axis. So if you needed that visual to help, hopefully that did. All right, moving on to question 8. The velocity in feet per second of a particle moving along a line, v of t equals t cubed minus 10t squared plus 29t minus 20, where t is the time in seconds. So we're going to have a bit of a scaffold question here. So we're talking about velocity, and it's being measured in feet per second. And the particle moves along a line. So we have this velocity where t is time in seconds. So t is time in seconds. Okay, so the first thing, A, how would you find a change in position of the particle on the time interval from 1 to 5? And what would be the unit of measure on that answer? So let's kind of set this up. So we're talking about a change in position. And as we do a change in position, all right, then we're going to have our integral symbol that's going to go from what are my boundaries? Where would I find the boundaries in this problem? I'd be looking right here. So it's going to go from 5, top bound of 5, lower bound of 1. And then the model right here is v of t. And then we would do dt. And then what about my units? So in this particular situation, it's a change in position, and the units would be feet. Now you could write this whole equation down here, but if it's defined as v of t, just using the v of t right here does maybe give you less opportunities to accidentally write something from up here down incorrectly. So you can use the name that's given here because that's part of the given information. Okay, so then in the second one, Part B, it says, how would you find the total distance traveled? And so if this is by a particle on the time from 1 to 5, and what would be the units of measure on that answer? So just set up again. I'm going to write my integral, and I'm going to get my boundaries from here. So that's going to be an upper bound of 5, a lower bound of 1. But because we're finding the total distance, then that's where we would have our absolute value of v of t dt. And then what units would I use in this case? And hopefully you can see that it would be feet in this case as well. So that just gives you an example of the two setups that we were talking about, where it is a change in position or the total distance traveled. So when you would use absolute value bars and when you would not. Okay, so next problem 9. This table goes with problem 9. Most of the time College Board will put their graphs right above the problem so you can make sure that you're using the right information. Well, actually, before I move on to that other one, I did wanted to talk a little bit about like a calculator kind of thing here. So if you need to pause your video for a second and run and grab your calculator, go ahead and do that. And so basically thinking about the graph of v of t, right? So as we're traveling to the right, we're going to go to the right, then a little bit to the left, then is its displacement positive or negative? It's going to be positive because it traveled more to the right than the displacement. So like if you're looking at, a graph, right? So maybe something like this. If I start at 1 and I'm going down here to 5, then it's maybe going something like this, and then maybe down here it comes back up, something along that line. So we're traveling to the right for a little bit and then to the left. And so that displacement would be less than the total distance. It's going to be positive, but it's going to be less than the total distance. So if you were going to do this on a calculator or kind of work through this problem on a calculator, then I'm going to put in y1, I'm going to put v of t. And then I can use that in my calculator to do this. So go ahead and pause for a minute and put in VT in your Y1. Okay, so we're going to put this in Y1. So we're going to go here and enter our velocity function in Y1. And then I'm going to go to my window because we're evaluating this from 1 to 5. So I'm going to set my window to go from 1 to 5. And then I'm going to graph. And so that's kind of where this graph I was rough sketching came from. So I got to thinking, you're probably looking at me going, where did that come from? So it's not math magic. It's just the function graph. It's just not a super pretty graph. So as you're looking at it, you can see you're traveling to the right and then it's going down. So it's kind of making that negative thing. But then we've got a little bit, but it was more positive than negative displacement. So we should be able to kind of see that. Now we're going to use our calculator to do both of these calculations. So on the first one, when we go from 1 to 5, v of t dt, okay? We're going to go into our home screen, so second quit, and we are going to do alpha window and pick choice 4. And then we're going to go from an integral of 1 to 5. And then remember how we put the function in y1. So we're going to do alpha trace, pick y1. And the variable that we're using is x. So when we calculate that, that is approximately 10.667. Okay, now if we do total displacement from 1 to 5 of the absolute value of v of t dt, and the calculator, that would be x's, right? Then we would go to our home screen, and we're going to do alpha window 4 again to get our integral. It's going to go from 1 to 5. Then we're going to do alpha window choice 1 to get our absolute value, and then alpha trace y1 to put it in there. And then remember, in the calculator, variable is x. So when I do that, then I get this one to be a little bit, 11.833. And so the total distance is going to be here, where the distance from subtracting the top and the bottom would be there. So just running through how to use that calculator again, because it has been a while since we did the calculator skills. Okay, now I'm ready to move on to number 9. All right, so on number 9, this is the table that goes with it. Pause your video for a minute, do your first and second read, and then we will work through parts A, B, and C. Okay, so you've made note that this bottom row is temperature. It's in degrees Celsius, T of X. The distance is in X centimeters, so we definitely have some units here we have to be careful about. And then we have a metal wire of length 8 centimeters, and it's heated at one end. The table above gives selected values of the temperature, and it says of the wire X centimeters from the heated end, and then it tells us the function T is decreasing, and it's twice differentiable. So basically, it's heating at one end, and the further you get from that heat source, the cooler the temperature. That's why it's decreasing. So if you're 8 centimeters away, according to the table, then the temperature has dropped 55 degrees Celsius on the wire. So that's what this information is meaning. So we're actually going to kind of look, I keep saying kind of, but we're going to look at this part right here in our table. And when we look at what's going on here, we're keeping in mind you're moving away, those kind of things. So it's real important. Remember, did we see any kind of initial condition in here? We did not. Anything else we need to mark up? I think we've got it all covered. All right, so on A, it says estimate T prime at 7. So do I have an equation to be able to do that with? No, so I'm going to have to estimate this by using AROC because I don't have an equation right here to do IROC, right? I don't have a derivative equation to plug that into to find the value. So we're going to use AROC to approximate. We're going to show our work that leads to our answers, and we're going to have our units on our final answer. So remember that oftentimes in problems like this, you may get a point for the difference quotient and a point for the answer. Sometimes it's 1 point for both. So if you leave off a unit, you wouldn't get credit for the answer because you didn't have the unit. So it's best practice just to remember to write down the difference quotient anytime you're doing that, so you're okay there, and double check and make sure and look for things like that indicated unit of measure. Okay, so having said all of that, let's do our IROC. So if we're looking at 7, 7 is between 6 and 8, so it's falling in this part of the table. So then I'm going to have t of 8 minus t of 6 all over 8 minus 6. Remember that you do the end of the interval, subtract the beginning of the interval, so you get your difference quotient in the right order. So then I get the numbers on the top from the chart by doing 55 minus 62 all over 2, because 8 minus 6 is 2. So on top, 55 minus 62 gives me -7, and I have a 2 on bottom. And on top, that is the unit that is showing degrees Celsius. And on the bottom, that 2 represents a length, so that's centimeters. So it's -7/2 degrees Celsius per centimeter, meaning when you are about 7 centimeters from the heat source, the temperature is dropping at about 3.5 degrees Celsius. Okay, so that was part A, using stuff we've been doing since the very beginning of school. So everyone should be totally comfortable with that part of the process. All right, so in the second part, it says find the integral from 0 to 8 of t prime x dt and indicated units of measure. So again, we're going to have measures in our answer. So we use the integral process, right? So it says it's the integral of t prime. That means if you integrate, you're going back to t of x. And you're going to evaluate that from 8 to 0. So I have t of 8 minus t of 0. Remember, we said whenever we're doing things in a chart, we're going to write down the values that we need from the chart before we go pull them out. So t of 8 is 55, and t of 0 is 100. And so that is -45. And what is my unit here if I'm only using the t values? It's going to be degrees Celsius. Okay. We're going to definitely need to keep that negative there because remember, this is a decreasing function. So that -75 degrees Celsius shows that dropping. Okay. So then 3, using correct units, explain the meaning of this integral in terms of the temperature of the wire. Okay, so using the correct units. So as you're thinking about this, think about displacement is no absolute value, and displacement or change in temperature. So you're kind of looking at those things here. So what I would say is the change in temperature in degrees Celsius from 0 to 8 centimeters. So I think we talked about this before, FUBUing your answer. Make sure you're saying where it's happening at, what are the units, what's the answer, what are the units, those kind of always keeping track of those units. So I'm going to say the change in temperature and then what's the units in degrees Celsius. Where is this occurring? From 0 to 8, and what are the units? Centimeters. So I don't need a dissertation. I don't need you to write 3 paragraphs to explain this. It should be succinct and to the point. Okay. Sometimes I know you guys just write a bunch of stuff down in the hopes that something sticks. If you do that, I'm probably not going to read your explanation. So keep it short and simple. Change in temperature, that's what's going on. What are the units in degrees Celsius? Where is it happening from 0 to 8? And what are the units there? Centimeters. Okay. So that's a very short explanation. That is all you need, my friends. Some of you are still writing me paragraphs to answer something that basically, when you do that, just tells me you don't really understand what's going on. When you can't be succinct and to the point, then you really aren't understanding those processes. So if you need to come in and talk to me about that, please feel free to do so. I'm happy to help you and make sure you get where you need to be, but I want really short and to the point answers. Okay, so pause the video for a minute, read question 10, wrap your mind around it, do your first read and your second read where you enter or mark up the problem. Pause now. Okay, so we've got a population of insects at a rate, and it gives us a function, and that function represents insects per day. And then we want to find the insect population after 6 days if the initial population was 35 centimeters. So we have an initial condition, so hopefully you caught that and you mark that when you're setting up. So as you're thinking through this, anytime that I see a setup or a setup for an antiderivative of a rate, it represents the displacement of the antiderivative of that rate. So in this case, they're giving you the rate at which insects are increasing. So what would a definite integral of that rate represent? Well, it's not going to represent the number of insects. It's actually going to represent the change in the number of insects. So it's the change in the number of insects. Okay. So as you can see, we have initial condition here, right? The initial condition is going to happen first. So remember, we do the initial condition. Sorry. Initial condition plus the change. Okay, initial condition is not an afterthought. It's not something that happens after, oh, I found the area. Oh, wait a minute, I'm going to go tack it on at the end. Tacking it on at the end, in my opinion, is not an initial condition. It's an afterthought. So when I see your setup, I expect the initial condition to happen first plus the change. All right. So in this case, what was the initial condition? The initial condition was 35. So that was this piece right here. So I start with 35 and I'm going to add to that the change. So the change would be the integration. So we're going to do the integration from on the population after 6 days. So I'm going to go from 0 to 6 days. And then the name of my function up here, I'm going to call that L of t. And then I would have dt. Okay. So what is this? This is the initial, right? The initial bugs. And then this is the change in the number of insects. So this is the change in the number of insects. All right. So 35 would not be part of the integrand in the dt, right? That's going to happen first. And that's one of the other reasons for remembering your initial condition first, because if this 35 is back here and it accidentally slips into the integral, then you could actually be doing a whole bunch of stuff that you shouldn't be doing. So it's the initial condition plus the change. And remember that you need to have this dt that kind of corresponds with what's going on here. So a lot of times this might be the last part of a FRQ where they're addressing the initial condition at the end. So just keep that in mind when you're doing your problems. Okay, the last section, guys, this is some accumulation of area. We have the shaded region A that has an area of 9.3, and this goes from 0 to 6 of f of x and has an area of 6.1. Use the information and the properties of definite integrals to answer the following questions. Definite integral is the area under the curve, remember. Okay, so we're talking about this area right here. So if I were kind of doing this problem, I know that I have, let me get some, just one over here so I can keep track. So we have this total right here of 6.1. And I know that the area of part A is right here, and that is 9.3. I'm going to call this B. And so as I'm finding the area for B, then take a moment and figure out what that area would be. So how could I figure out the area under the curve? And then we will go from there. So take a few minutes and kind of wrap your mind around this problem, and then come back and we will work through it together. Okay, I just want to give you a minute to kind of read through because there are a lot of different things happening here. So let's start by coming back and finding the area of B. Okay, so the area of B would be this part right here. So it tells us the total area is 6.1. It tells us part A is 9.3. So what could I do to find B? I could take the total area of 6.1 and I could subtract the A area of 9.3. And that tells me that it's going to be negative 3.2, which makes sense because it is below. So actually, if I look at this graph now, I'm seeing right about here, it looks like that's at 3.5. Everything else kind of looks fairly good, I think. Sometimes when we move in the picture there, some of the lines can get off. So I just wanted to double check. Okay, so first we're going from 0 to 3.5. So we're going from here to here. That's all of this is that we have labeled A. So then in this problem, we know that the answer for this is going to be 9.3. And this is area A. All right, so that's a given. So now we're going from 3.5 to 6, which is right here. So that's our B area. We just found that a minute ago. And so that is negative 3.2. All right, so now we're going to find the area from 0 to 6, but notice the absolute value bars. So that just means the total area. So I need to add up the total area. So I'm going to add the 9.3 from A to 3.2 from B. And when I add those together, I get 12.5. Okay, so why don't I worry about the negative? Because absolute value bars tell me not to worry about the negative, and that's just the total. So I'm adding A plus B. All right, so then I get down to my next one right here. And so I'm going to go ahead and pull my negative 3 out here and go from 0 to 3.5 of f of x dx. And so what am I looking for on the graph? Right? I'm going to take a minute and think about where would I get this information from that graph. Okay, so hopefully you saw we're going from 0 to 3.5. So 0 to 3.5 is in fact just area of A. So then what I'm doing is taking the area of A, which is negative 3, the area of A, which is 9.3. And because I was able to pull the constant with that negative out in front, all I'm doing is finding this is area A times negative 3. So when I do that calculation, I get negative 27.9. All right, so then I can move on to E. So again, I have a constant, and because we're using separate little areas on the graph that we've broken it up into certain intervals, I'm going to go ahead and pull that 4 out in front. And so I'm going from 3.5 to 6 of f of x dx. All right, so now what am I looking for? I'm going from 3.5 to 6, so now I'm talking about this area down here. And so that area down there is negative 3.2. And so I'm actually saying I'm going to multiply the area of 4 times b. So I'm going to multiply 4 times area b. So then I get 4 times negative 3.2. And so my total area then is going to be negative 12.8. All right, last one. So I have a rule here. What is the rule when we're adding two things together? That we can take the integral of each one separately. So let's go ahead and get that set up. So I'm going from 0 to 6 of f of x and dx. And then I'm going to add that. And let's go ahead and pull the 3 out in front and go from 0 to 6 of dx. All right, so I want you to pause your video one last time and calculate the area for this problem that we just set up. Okay, so I know when I go from 0 to 6, I was told in the original problem that that's 6.1. So I know the area for this piece is 6.1. And then I know this one I'm going to take 3. And we know that when it's just 1 dx, we can subtract the boundaries. That's the property, right? 6 minus 0. So I get 3 times 6, which is 18. 18 added to 6.1, which is 24.1. You could also have used the fundamental theorem of calculus on this one. And if you were going to do that, and then this is the other option, then you would be going from 0 to 6, 1 dx. And so then when I take the antiderivative or find the antiderivative, that's 1x to the 0. So that just becomes x. And then we could evaluate it from 6 to 0. And so then I'm going to have plug in my 6 for my x, and then I'm going to plug in my 0 for my x, and that's going to give me 6. So that is either applying the fundamental theorem of calculus if you did it this way, or just using the properties if you did it this way. So in this case, at that point, you had a couple of options. All right, so hopefully this wasn't too bad today. A lot of setup, a little bit of language. Your daily practice are these problems right here. On 101, it's just setup only. The rest of these are actually working them. So these are textbook problems, so you can find that on Canvas. All right, guys, I will see you next time for part 2 of Fundamental Theorem of Calculus. Bye.